All right, and since we're, I think, moving well into the discussion, I guess one kind of open question, because I know there's a lot of gravity and EHT people here. What are the plans, if any, for simultaneous observation?
Jason, I think that's a question for you.
There was one, right? Wasn't there one, some overlap?
Yeah, we planned it. Yes, I think 2018.
Yeah.
Yes.
Yeah, I mean, Fariel, I think you know probably more about this than I do, but I think the scheduling is really difficult. So I think a lot of people are very interested in making this happen. It's an obvious thing to do for Sagittarius A, and it would be pretty powerful for, reasons Alejandro just outlined. You could try to get at the magnetic field, for example, 2 different ways. Figure out where these flares are, what's going on. I think the scheduling is one immediate issue, right? That the EHT needs good weather all over the world. In this one observing window, the VLT is a major optical telescope facility. It's not easy to get exactly what time you want, and gravity also needs good weather there, right? So I think it's mostly set by practical considerations. The EHT should try to observe when the moon's really bright, because that's when we get gravity nights, because we're observing in the infrared. Anyway, I think a lot of it is practical, and if we keep doing it, probably it'll happen more and more. I'm honestly not sure I don't have any sense of the EHT scheduling. I'm sure it's very highly constrained as well. I mean, just ALMA would be quite constrained as well. So.
Yeah, I mean, as you know, we propose for ALMA time every year, and they give us a window of so many days over which we can trigger or not trigger. And our multi-wavelength group works very hard on lining up all the other observing proposals to get time once we know that window. But I mean, we also observe simultaneously with Chandra and many other observatories and some other ground-based gamma rays, etc. So we can't change those schedules last minute, but I think we basically say, here is the observing plan, and go and hope for the best. Gravity is the one that I haven't been personally involved in at any point coordinating. So I'm not sure how the connection works there.
It's a similarly constrained and difficult scheduling.
I have a very dumb question that might reveal my ignorance of infrared stuff, but is there any would there be any reason to, or could we learn anything by observing M87 with gravity, or is that just not feasible? Just a random question.
If possible, I don't take all these. Felix and Sebastiano, I see you there. I don't know if you're there, but if you want to chime in on any of these, you're welcome to.
I'm actually not sure. We had the discussion about M87 at some point. I guess there's not much to see with gravity, but one would have to ask other people or do the calculations. I'm not entirely sure.
Yeah, my recollection is the infrared in M87 is pretty faint for gravity.
Yeah,
infrared interferometry standard, but I also agree with you, Felix. I'm not sure what exactly we expect to see. I mean, jet of some kind, but I don't know.
Also interesting about Sagittarius A is the timescales are really short broadcasts. That's immediately different on M87.
Yeah, I'm just wondering if there was some infrared. Oh, sorry. If there was some infrared stuff going on at the jet base, if that could be tracked with gravity, that would be cool.
I was just going to say, indeed, for M87 to see things on dynamical timescales, you would need days-long observations or to come back repeatedly to see how the characteristics of that is changing. But yeah, so I mean, even if we have the spatial resolution to M87, probably the type of flaring activity and spatially resolved motion that we see in Sagittarius A would not be possible because of its mass.
Yeah, I think the limiting factors maybe in order, I don't know, but brightness and then having a phase reference, right? Because you would then, as you say, you would then be probably needing to do astrometry like night to night, like is done in the galactic center for, you know, S2 or the stars. And it's unlikely that there happens to be a reference source nearby. But it is interesting for the future. Felix and Sebastiano, you guys should look into it for Gravity Plus days ahead. There's an upgrade planned that will start soon to go to much fainter sources.
Oh, you weren't joking. That's nice.
Are there any other things people want to bring up from either this session or the earlier one?
Can I ask, so as an ideal MHD person, I am intrigued, Bart, I know we've talked about this before, so sorry to do it yet again. Do we all need to be doing resistive MHD? So I thought in particular your comment at the end of that first session was super interesting about the motivation for the resistivity, which I had not, pardon my ignorance, I just had not appreciated at all. You made a comment that whether in ideal MHD or resistive MHD, that getting to this critical resolution of having a high enough magnetic Reynolds number might be sufficient to see plasmoids. So do you think you would really see, you would expect to see plasmoids in ideal MHD if we went to high enough resolution? Is that, did I understand that correctly?
Absolutely, yeah, no doubt. I also ran my simulations with ideal MHD, and they look visually exactly the same. The main difference is that the current sheet at some point in resistive MHD is resolved. So you know it has a certain thickness, which is related to the resistivity that you set. And that thickness you can then resolve by, say, 10 cells so that you sort of can trust the evolution. But in ideal MHD, you will see that this current sheet will also exist, but it will just be thinner because it will collapse to 1 or 2 cells. But globally speaking, it will do the same thing. You can do ideal MHD for like to look at the global dynamics, and I think to a certain extent you can even trust the heating due to numerical reconnection, let's say. The main thing you cannot get is a parallel electric field because it's hard coded to be minus V cross B, so there can be no parallel component in ideal MHD, and that parallel electric field is what accelerates particles. So if you were to run an ideal MHD simulation with test particles, you would get practically nothing unless you give the particles some kick out of Maxwellian by hand, let's say. And I think that's the main difference. So you need to do a library of ideal MHD simulations, and then you need to do your most realistic ideal MHD model with resistive MHD and test particles. You don't need to do a whole library of resistive MHD simulations. That would be my take.
That would actually be very interesting to, if you have a high resolution ideal and a corresponding resistive simulation, put test particles in both, and like you said, just randomly kick the particles in the ideal one, and you get, you know, statistically the same result. Kind of an experiment that should be done at some point.
We are doing such experiments in like decaying turbulence in a box, and you see in ideal MHD it's very hard to get like a tail in a Maxwellian because this kick would have to be very specific. You know, it depends on the Larmor radius compared to the current sheet size, etc. And that's hard to mimic if your current sheet size is resolution dependent.
So I think I have a very unrelated question and maybe super dumb, but is there any chance to see other, like, if we say that generation of plasmoid in a jet or whatever is like not something that is particularly expected to be in Sagittarius A star, but also in other objects, could we see kind of like hotspot signature in polarization in other objects, like some, I don't know, AGN, low mass binaries or whatever? Like, is it even possible, or I know resolutions you would need would be super high? Like Alejandra, what do you need for a resolution in your gravity? Like, if you were to see like 100 RG, would you still see that signal, for example, or would that be?
I'm sorry, can you repeat the question?
Yeah, because I'm wondering, like, how much of a resolution you need to see a signal, like you showed, like the loop, two loops, or stuff like that, and in the polarization, and depending on that answer, like, is there any chance to see that kind of signature in any other objects than like Sagittarius A star or M87?
So let me jump in for a second while Alejandra is thinking about what gravity needs. Certainly there's a lot of study of reconnection in other communities, in other regimes. I mean, solar physicists have studied reconnection for a very long time. People have tried to understand it in the blazar context. So there are just many different regimes. I wish I had a plot of sigma versus beta, for example, and where different objects lie. We are in a unique regime there, trans-relativistic, etc., the particular betas that we have. So trying to understand how reconnection works there and how it leads to particle acceleration is new, but not in the context of all the other work that goes in the field of reconnection. So I'm sure there is polarization signatures that's been considered for those types of objects. Maybe, I mean, for the sun, of course, we can do spatially resolved everything, but I wonder what aspect of blazar polarization, for example, we could use to constrain it, and whether that would teach us something about the regime that we are interested in. These are really interesting questions.
You have even the other side of the spectrum in pulsars and magnetars, where you have highly magnetized plasma that shows plasma formation resulting into radio waves, for example, coherent radio emission.
Mm-hmm.
Yeah, I guess for gravity, so I'm not sure, I guess. So these flaring events last from 60 minutes to 80 minutes or so. So if you do have, say, something that it's moving, I don't know, say this hotspot or so, it would have to survive at least this 60 to 80 minutes, right? So there are some other simulations. For example, Jason has a paper where from one of these MAD simulations, this powerful ejection is, yeah, like thrown out by this buildup of magnetic field, and so you have this over density that is going around the black hole. Also, yeah, like Oliver Porth has a similar paper, and I think they do manage to get these over densities, say around the black hole, that last, yeah, over 60 to 80 minutes or so. But the problem there is that the radius at which they are is very close to the black hole and not farther out as we see in gravity. So I guess observationally, you would want maybe a faster time sampling or so. So that you can see between two loops or one loop, or maybe there's a tiny in-between loop or so. But yeah, I'm not sure then. Yeah.
Any other comments, questions, requests for the observers to do something, requests for the theorists to do something?
Well, I would like more rotation measurements. M87, please.
I guess along that line, I have a question for Angelo about the rotation measured as star. Have you looked at any of these models like that you did for M87 specifically for Sag A star, and like how much rotation measure would they produce relative to what is observed?
Oh, so that study was just for M87. Should be relatively.
I think it'd be cool to check because you mentioned that you have the picture of it being most of the rotation measure being an external screen, and if it turns out that these models like automatically when you plug in the Sag A star flux density produce a rotation measure much lower than what we see for Sag A star, that would be a pretty interesting, right? Whereas they seem to do pretty well for M87 in terms of values.
Right. I'm hearing enough silence. I think, Sean, should we wrap it up for today?
Yeah, I think that's good. It's right on time, so.
Yeah. All right. So thank you everyone for showing up. Thank you for our speakers and all the discussion we had. So tomorrow is more about flares, tests of GR, and particle heating. So see you all then.
Thanks, everybody.